Hi everyone, I hope you are doing awesome. In this video, I'm going to review attention mechanism. Imagine you're in the middle of a duel facing your opponent under the scorching sun, with adrenaline rushing through your veins. Definitely, you focus on your opponent and ignore the majority of what's in your field of vision. Okay, let's forget about this violent example and stick to more educational ones. Assume you're reading a paper about machine translation. Your focus is directed to the words that you are currently reading, and your visual processing system disregards the other parts of the text. Inspired by this cognitive functionality of the human brain that allows ignoring irrelevant information, we can make deep learning models to attend differently to each part of the input by assigning an attention weight to each based on their relative importance to the specific task at hand and direct more focus to what matters most. For instance, a deep learning model that attempts lip reading should pay more attention to the lips and lips movement rather than other parts of the mouth-centered cropped image. Or in a machine translation task, to predict each word in the target language, we should guide the model to pay significant attention to parts of the sentence in the source language that play a vital role in this prediction rather than other words in the input sentence. This is how attention mechanism in deep learning works. Let's dive deeper into the topic and see the added values that utilizing the attention mechanism can bring to machine translation and sequence-to-sequence modeling. The traditional machine translation methods use sequence-to-sequence models with an encoder-decoder scheme. In these models, recurrent neural networks are used to design encoder and decoder architectures. RNNs return a hidden state in addition to their output, and this hidden state is passed to the model while processing the next element in this sequence. In RNN-based encoder-decoder sequence-to-sequence models, words of the source language are passed to the RNN encoder one at a time sequentially, and the last hidden state of the encoder, which is regarded as context vector and assumed to contain all the information of the source sequence, is passed to the decoder. The decoder attempts to translate the sequence in the source language to the target language conditioned on this context vector. Using the last hidden state of the encoder leads to a serious problem arising from the fact that a long sentence conveying lots of information cannot be entirely distilled in the last hidden state of the encoder, since recurrent neural networks suffer from the incapability of preserving long-range dependencies. For instance, assume you are attempting to translate the sentence "stick to your diet and don't eat that delicious pizza" to the Persian language. The information of the words at the beginning of the sentence is almost forgotten, and only the phrase "eat that delicious pizza" is encoded in context vector C. Translation based on this context vector might lead to an inaccurate or even incorrect sentence in the target language. The solution to alleviate this issue is to make an enriched context vector conveying the information of all elements in the source sequence and allowing the decoder to access all of the hidden states extracted by the encoder. In this regard, one can simply sum up all the encoder hidden states in order to achieve an enriched context vector. Although this context vector can alleviate this issue to some degree, but it's not the smartest choice. Assume you want to translate the sentence "stick to your diet and don't eat that delicious pizza" to Persian. As you can see, the sentence in the source and target languages are not completely aligned, and there exists a huge misalignment between these two sequences. Moreover, different words in each sequence interact with each other differently, and to predict the correct equivalent word for pizza in Persian, the words "delicious" or "eat" are much more relevant than the words "that" or "stick to." The different degrees of relevance between different words should be taken into account in the procedure of achieving an enriched context vector. The wiser solution to enrich the context vector C is attending to each element in the sequence differently and calculating C by a weighted sum over all hidden states of the encoder. This is the idea of attention mechanism, which was introduced in the paper entitled Neural Machine Translation by jointly learning to align and translate for the first time. Now the question is, how are these attention weights alpha i's calculated? Assume you want to predict the word y2 in the target language. The previous hidden state of the decoder, HD1, and all the hidden states of the encoder should participate in calculating context vector C2. Note that superscript E denotes the encoder and superscript D denotes the decoder. More generally, to predict the element yi in the target language, a context vector ci should be calculated based on the previous hidden state of the decoder and all encoder hidden states. Also, a similarity function is needed to determine the attention weights. There are lots of similarity functions that we can use. For instance, cosine similarity and dot product are two popular ones. At first, a similarity vector should be calculated, and each entry of the similarity vector, Sij, is determined based on the similarity of Hdi-1 and Hej. If the dot product similarity function is chosen, each entry of the similarity vector, Sij, is the dot product of Hdi-1 and Hej. Then, the softmax operation is applied to the acquired similarity vector to attain the alignment scores or attention vector alpha. Finally, the context vector Ci is simply calculated by summing all encoder hidden states weighted by attention weights alpha i's. This interesting figure denotes how attention weights help translation from one language to another. The order of translation of European Economic Area should be reversed in French, which is denoted by alignment scores, as you can see. In summary, attention mechanism is a fancy name for weighted average and attending differently to each part of the data by finding a set of attention weights based on the relative importance of each part of the input to the specific task at hand. Thanks for watching. I hope you find this video valuable and educational. If you like this video, please subscribe to my channel.